Good afternoon, everyone. We're the FUNSAT design competition and near Earth Explorer Club. I'm Jonathan Groot, this is Newman, and Frosik. Our graduate mentor for this project was Shinde, who's here today, and our faculty advisors were Professor Tosunoglu and Professor Tansel. So to give you a little overview of how we're going to approach this problem, we're going to give you a brief introduction into what was asked of us in terms of the competition. We'll each go through our subsystems, and then we'll just give you a conclusion and open the floor for questions. So for the motivation behind this project was obviously the FUNSAT design competition, so we're given certain constraints and parameters that we had to follow. We just simply had to design a satellite that would be used for weather research, so it would be launched into orbit and it would take videos and pictures and thermal images, and we would use that for weather predictions and fire hazard prevention, etc. The constraint that was given to us, it was a 3U cube satellite, which is 10 centimeters by 10 centimeters by 30 centimeters. You can picture that it's really small. The weight that we were allowed to go to was 4 kilograms, nothing over. So we're trying to keep it as light as possible. And all our standards conforms to Cal Poly, which is the standards for the cube satellites. So for the structural design, we were going to do a structure that housed all the essential components within the constraints. We're not allowed to go beyond those constraints. What we're going to do is we designed it so that it was the center of mass of the entire thing was around the geometric center, so that when it's launched into orbit, the attitude control system can more easily adjust it in the orientation that we want during its orbit or rotation around the Earth. So how we did that, how we approached that, we don't have all the components because it's an ongoing project, we have most of them. So what we did is we researched the dimensions of each part so that we know they would fit. We researched the mass of each part, and then we created the relative density so it would give us the resulting mass in SolidWorks, and we carried out simulations. And we also oriented it within the satellite so that the center of mass would be around the geometric center, and we had to make sure that that was capable with all the components that we had to do. So this here is a screenshot showing the mass properties that we achieved moving them around within the satellite. Essentially what we were looking for was 0 millimeters in the X and the Z, and 150 millimeters in the Y. It was 300 millimeters high, so we're looking for halfway in that range. As you can see, we came very close, which is within the standards, the plus or minus 2 millimeters standard set by NASA. So we were very close to achieving that. We know that when we actually build it and put all the components inside, we can achieve that. So this is just a design process showing you the stages we went through in developing the structure. This first image was the structure that the previous senior team did. Our goal was to take that, see how we can make improvements to it. So initially we started with a removable structure. That was the design you can see here, where we had 2 modules so that during testing, it was easy to access all the components within the structure and make changes to them as needed. But as we progressed, one of the things that changed was the length of the lens, as the previous senior team was doing. So the lens became longer, which rendered that almost impossible. So, and also for this design here, we were only allowed 2 solar panels in each recessed panel because the solar panels are not allowed to go outside the constraints. So because of that one bar, they were only allowed to fit 1 solar panel in each one, so that's 2 on each side. What we needed essentially was 3 on each side and 1 on top, resulting in 13 to generate the necessary power to run the satellite during its orbit and lifetime of there. So moving on, we came up with a slightly different one by adding that extra bar there, which increased the structural integrity beyond what was needed, but it was necessary in order to fit the components. So we came in at a pivotal point between competitions. So the competition is held every 2 years. So the end of our senior 1, the last competition was held where we worked along with the other senior 2 team. And now moving forward into our senior 2, we pretty much set the base for teams coming onto the project. So what we have here, this is the poster from the FUNSAT competition, which was a collaborative effort between us and other teams, which was led by Pradeep. And this shows all the testing and stuff from this structure that we did. So from the competition moving onward, we changed a few things, added more solar panels, and this was our final design in terms of structure. So in terms of actually constructing it, to construct the chassis, it was just, we took the bars and milled them down to size. The bars available to us were 3/8 of an inch. which was 9.5 millimeters. NASA set a minimum requirement of 8.5 millimeters for the cross-sectional length of the bars. So to save on weight, we went to that minimum of 8.5 and removed that, and then it's just a matter of cutting and welding it together. This just shows the rough chassis as it was welded together. We did aluminum brazing, which is using a gas torch. So for future developments, going on to other things, what we found with this welding was that the gas welding took a lot of energy and a lot of heat because aluminum is very good at conducting heat. So over time, as you move from one weld to the other, it started to warp the structure somewhat. So at the end of it, there was a lot of reheating and straightening the structure again to get it back to its original size. So one of the things going forward would be to look into alternative welding techniques that would do it more efficiently, because we spent a lot of time applying the heat just to get it up to the right temperature, and also it would make the welds a bit stronger. Another road to take would be a modular build where there's no welding to do the components where they connect with brackets and screws, etc.
All right, so now we go on to the attitude control. So first off, what exactly is attitude control? Attitude control is the means by which the satellite will control its pointing and orientation in space. Also, when it's deployed, it's essentially thrown into space, and as such, it's the means by which it will de-spin and come to a neutral position. So how do we go about doing this? Now, there are numerous ways to implement attitude control. There are numerous actuators that you can use, but for a project, we decided to go with magnetorquers, also called magnetic torque bars due to the cost of them. How it works is it's essentially a solenoid, it's a coil, solenoid type coil with a magnetic material as its core. When a voltage is applied across the solenoid, we know from basic physics that magnetic field is created. And through interaction of Earth's magnetic field with created magnetic field, what happens is they try to align themselves, which creates a torque that acts on the body of the satellite that's pushing it. So when we have one of these magnetic torque bars in line with each principal axis of the satellite, we are therefore able to control its orientation in each direction. So now we go to our design. Take note of the length and radius and the permeability, which is a material property that was defined for us based on market availability and also the constraint put forward by the competition. We then went on to define the wire radius that we use and the amount of turns to make this coil, and we calculated a force of approximately 42.7 newtons. So now we ask ourselves, what is the significance of this force and what does it actually mean? And what we did, we tried to relate it back to a time relation using impulse momentum equations. And defining a 1 degree rotation, we did an analysis and found that it would take approximately 12.3 seconds to rotate the satellite by 1 degree about any axis in the defined time there. So now we actually go on to the construction of the attitude. Here we used a perm alloy rod as its core. We had approximately 1,400 coil turns, and we used a drill and actually inserted the core into the drill and then fed the wire by hand. And we counted the layers that were created over the length of the rod instead of the actual individual turns. So that's the method that we used. And then we go on to see the testing of it. I will point out that the proper way to test these torque rods is actually to use a set of Helmholtz coils. Because Earth's magnetic field is very strong on the surface, you run into problems when actually trying to measure the magnetic field with a magnetometer. What the Helmholtz coils will do is actually cancel the effect of the magnetic field, and you're actually able to create and control the magnitude of the magnetic field where the torque rods will be tested. And we actually defined an experiment and designed an experiment, but due to the lack of availability of equipment, we had to go with a simplified method where we actually just measured the magnitude of the magnetic field created around the perimeter of the bar, and we applied different voltages to test the consistency of each bar. And it was confirmed that the torque bar was reacting accordingly. And here is just a breakdown of all the construction, because the structure and attitude control were the only parts that required any fabrication. We actually came out to a total cost of $410 for both parts.
So now I'm going to talk about the orbital parameters of our satellite. In order to accomplish the mission that we set for ourselves, that is Earth observation, we want to have it as close to a polar orbit as possible, because a polar orbit would give us coverage of 100% of the Earth's surface as we go in orbit. also choose a sun-synchronous orbit on top of this. And the reason for that is because the sun is in the same point at the sky every time that we cross the equator. So if it's directly overhead on one cross of the equator, it will be directly overhead the next time we cross as well. And we choose the orientation of our orbit to be in the dawn-dusk plane. So what that means is that it's in the plane of the sun shining onto the Earth, which means that our satellite is going to be bathed in sunlight constantly as it goes around the Earth. We choose an altitude of 600 kilometers because that gives us a large coverage of the ground, and it also increases our time in the sun. In order to achieve a sun-synchronous altitude and orbit at an altitude of 600 kilometers, we require an inclination of 97.79 degrees. At the time of launch, the right ascension descent node would be 102.7 degrees for the simulation that I did, with the argument parity of 0 degrees, and with all of these orbital properties, that gives us a period of 1 hour 36 minutes for a single orbit. I know I just threw a lot of information at you, so here's a visual representation of everything I just said that shows our orbit, and as you can see, it is in the plane of the sun shining on the Earth. We have our ground station here in Miami on the roof of the Green Library, so that's the point that you see over there. And then here we have a 2D projection of the orbit onto the surface of the Earth. Now we use the information from our orbit to figure out how much power is being generated through our solar panels. So the way that was accomplished was we took the model that we built in SolidWorks and then we imported it into this program called Moto. And what Moto allows us to do is to define the solar panels, and we can also define the properties of the solar panels as well, so we get all that information from the manufacturer. And then we import that into the program SDK. And SDK has a module that shows you how much power is being generated by your satellite. So here we have an image of the satellite in orbit. You can see the 3 solar panels. And then here we have the graph of the power generation. The red line at the top is the total power, and then the contribution from each face is seen in each of the lines below it. And as you can see, the green face is the one that is most constantly being shined on by the sun. If we have a rotation in our satellite, or if we have a different orientation, then the lines will be different, but we can expect a minimum of 7.5 watts to be generated and a maximum of 8.5 at the level that we defined. Now, I'm also going to talk really quickly about the communication system of the satellite. So we have our ground station at the Green Library, and we need to be able to download the information from the satellite, that is its orientation and any data that it takes in the form of thermal pictures and optical pictures. So we need to be able to download all that information. And on the satellite side, we accomplish that by having an omnidirectional antenna with transmitting using the battery power. We're going to be given a frequency by the FCC in that data and a satellite tracking number. We're given that information from the FAA, the FCC, and that allows us to establish communication with our satellite. Now, the strength of the signal depends on the angle of the satellite relative to the horizon, and also on the design of the antenna. So the first antenna that we designed is just a simple listener using an egg beater type antenna. And the advantage of this design is that it's cheap. We can spin it up really quickly if we wanted to, and we can test it by listening to other satellites by tuning into their frequency. But the disadvantage is that we cannot transmit data to our satellite if we do that, so we can't really change our orientation. All that stuff would have to be pre-programmed. You can see the gain pattern over here in the bottom left, and there's a very good gain between 30 and 60 degrees, which is really what you want for a listener antenna, because you're more likely to have the satellite passing within those angles than directly overhead. So that's the advantage of this particular design. The cost over there. That brings us to the second design option, which eliminates the disadvantage from previous one that we cannot transmit data. This one can transmit data, and the other advantage of this is that we have it sitting in a warehouse through the NDE club. It uses a rotating nugget type antenna to listen as well as to transmit. And it also has a greater coverage because we can rotate it to follow the satellite as it moves across the sky when it's passing overhead. The disadvantage is that it requires more space on the roof of the the Green Library, and we would also have to rewrite the programming of the antenna. And here you can see that design with the game pattern and the design details. Now I want to talk about the FUNSAT competition that took place in May. We were there and we presented much the same information that you've seen here in this presentation, along with the Senior 1 group, and it was very good from a global design perspective as well, because we really got to talk to the people at NASA and a lot of international people there, and also we got to talk to the different schools that were also a part of the competition, get some ideas, exchange ideas, so that was a very positive thing, and we were the first runner-up in that competition, which gave us $3,000 to play with for future development. So the satellite is going to be in continuous development through the NEE Club, and I'm sure you've all seen the presentation. This is one teaching and one teaching has work. So those are presentations.
So you guys talked about your power generation for your solar panels. How does that relate to the power budget required for your satellite?
So we have we calculated how much power is going to be required at the maximum range, and that's going to happen when we're transmitting data. So what we wanted to do was make sure that we had enough power to transmit data. And so we don't have it on the slide, but if you look in the paper, we have the power budget, and we make sure that we're able to have enough power for transmitting data.
What's the expected life of your satellite?
About 2 years.
Okay. Did you guys consider any sort of radiation hardening of your solar panels? Because even in low Earth orbit, they will suffer significant power degradation.
We made sure that the solar panels that we chose, the manufacturer that we chose, is space rated.
So, from my experience, space rated is something that flies into space. GoPros are space rated. Especially for something like this, I would try to do your research instead of just trusting blindly what the manufacturer says, because a space rated solar panel will cost you 10 times more than a terrestrial solar panel, and in reality, they don't provide anything more than we need. Considering that your life is about 2.5 years, you could probably use a terrestrial solar panel and save yourself 10 times the cost without using space rated products.
And the ones that we chose were specifically designed for big satellites.
But we'll definitely take that recommendation.
Yeah, I mean, yes, SpaceX as a company has an entire team devoted to solar panel development, and their conclusion is pretty much like space-grade solar panels are a joke. So it would be nice because then you can save some money on that side and be able to throw some money into other aspects of the project.
So it's a kind of future. Unfortunately, we haven't actually purchased the solar panels, and so we'll be able to kind of.
What's your expected date of launch?
So we've been looking at different launch partners. There's a number of companies that are launching into sun-synchronous orbits. I know that ULA has satellites that launch into that kind of orbit. We're going to need to know the givens of the orbit from them. We're looking around 2018, 2019, so it sort of coincide with the next FUNSAT competition. We are at a very advanced stage of development, so this is going to happen for sure.
Talk to me about significant figures. Now look at your altitude control subsystems. I'm looking at numbers that have what, 1, 2, 3, 4, 5, 6, 7 significant figures. Angular velocity, same thing. Magnetic moment, same thing. Is that even possible? Is that measurable?
It actually is not that possible to get to, how should I say, that exact measurement.
So why are you presenting that? Let me ask it that way.
Okay.
You should be presenting what you're capable of.
Right, because we haven't tested it properly, we haven't actually been able to compare it to anything as yet. So when we actually do test it, we would have been able to present a a difference in what are theoretical versus are practical. But because we haven't done that yet, we just figured it would be best to just present the theoretical as we have it.
Well, and a lot of those numbers are a function of taking a measurement and multiplying it by another measurement.
Right.
You're never more accurate than the least accurate measurement. So that's what practice is. In your ideal orbit, you said your inclination was 97.79 degrees. Can you measure that?
So the inclination is really, we can't control our orbit. So what we did was a theoretical analysis based on what we would like to have. But what we're going to have is going to be Venus as far as partner. So whatever orbit that they launch into is the orbit that we're going to have. We're going to need to run the simulation.
And it's going to probably be at least, and probably inaccurate to a few degrees, probably.
Right.
Okay. Can you put up your first slide that had the picture of the full assembly?
This one here, or?
No, well, yeah, I could work with that one. I'm sorry. If I come over to the picture of your final design. Your centroid is down the middle of the device, but your moments are not balanced. So if this thing starts to rotate, it's going to continue to rotate because your masses are all on one side, they're not balanced.
No, so what we have is you have a lot of different components that have different masses. So how we oriented them was that we have that mass down the center of the structure itself. Once that starts to rotate, that's where the actual control system comes into play to counteract any sort of
But you wouldn't have to do so much work if, for example, the two black modules were 90 degrees relative to the two white modules in that system. So that now you've got fairly decent uniformity in the moment arc, for example.
Yeah, thank you. That is noted. However, the two black modules are the beagle bones, which are lighter modules compared to the two gray ones, which are the batteries, which in relation to those, they weigh a lot.
Yeah.
And then, so those smaller masses, they're offset, as you notice, the lens is off to one side too. The lens is a bit heavier, which also has the cameras on top, which adds to that weight that's offsetting the other sun sensors and stuff on the other side. So yeah, we do have a lot to play with once we actually construct that and insert all the actual components inside and play around with them and see how that weight actually affects it. But yeah, thank you. Yes.
If you could worry about your center of gravity later, could you make a better layout for your CubeSat on the inside? So do you have excess mass right now in your design? Are you at 4 kilograms right now?
No, we're below 4 kilograms. I think you could actually be able to answer the exact figure that we're at.
2.3, right? Okay. So my question is, instead of focusing on trying to balance your components, why wouldn't you consider adding ballast to your satellite so that you can place the components for integration, for usability, for accessibility, and for ease of design, and then deal with the center of mass later by adding ballast, which is something that most aerospace or spacecraft do.
That is something we can look into, and that's a very good suggestion. As long as we have, right now you just see the components without all the wiring. Once the wiring goes in, it takes up a lot of that, a little bit of free space we have to play with. As long as we have that space, once the wiring is done, we can add ballast inside it. We can't, the problem is we can't add anything to the outside, because during launch, it fits into a certain space, and we have those constraints. So as long as it allows for that in the end, so it's going to be assembling the components first. If it allows for that, then you can add the ballast and then reassemble after.
Are you concerned about how hot your satellite will get, considering it's always going to be pointing at the sun?
Right. We did do some thermal analysis and stuff on the satellite, and there's going to be some insulation stuff applied to the satellite in terms of air gel, and I know we're experimenting with different materials to try and stay this best, because yeah, it's going to be facing the sun. At least one face is going to be facing the sun at all times. So that is something to take into consideration during our testing.
So I'm going to ask the same thing I asked the last CubeSat guys. If you're insulating your satellite, how are your batteries going to work if they need to be in the temperature range? Like a specific temperature range to work successfully?
Meaning,
Radiator.
right. control the temperature with
Yeah,
the
because you're
satellite
insulating your
itself.
satellite, right? So
Right.
now your batteries are going to be cold, and they don't work in cold, right? You're going to be at negative 150 C in space, and your batteries work between 0 and 50 C, I believe.
Yeah.
So how would you fix that problem?
Yes, we'll have to put in a reheat to heat up the batteries and keep them running at the optimal temperature.
Or you could balance your insulation.
Right?
Or you could balance your insulation just so you get the temperature at
From the sun.
the temperature that so you protect it enough so it doesn't damage it, but at the same time you're not isolating it 100%. Now, have you been taking into account, since you have spent so much effort into the weight balance, have you taken into account the weight of the wires and the weight of the insulation?
We have, again, we don't know exactly how much wire we're going to be using. We came with a ballpark figure. That's why we're below the minimum requirement. So we know
But
we have.
for the balance of the weight.
Right. Well, yeah, we didn't take that into consideration because we're not sure exactly how all
Okay.
the wiring is going to be done. So once that's done, we'll have to do a bit of adjusting during testing. Yes.
So my job is to do the wiring for satellites.
Okay.
I would highly recommend that you have someone look at this while you're designing your structure, because it is a nuisance wiring. I agree, but without it, your satellite doesn't function. And you want to make sure that you have nodes so you can attach your wires successfully, so you don't have your cables like flopping around hitting your instrumentation. Your wires are very sensitive to temperature. And unless you want to add a lot of weight by insulating your wires, you need to make sure that they're placed intelligently. And I think that your harnessing system will save your design in a lot of places because, for example, like in the previous group, you just added heater to your batteries, and that solves your heating problem. But that's something that you need to actually design in, because if not, then you don't know what your power budget will be, you don't know how you're going to actually put it together. And then it's going to be an integration nightmare for the team that follows you. And then, unfortunately, if your wiring doesn't work, then your satellite won't function. So I would focus on the avionics portion of the project, or set like some sort of guidelines for the next team to do that, because without avionics, you're not going to fly.
Taking that into consideration, you should probably get your contact information.
Yeah.
Any other questions? All right. Well, thank you very much.